Hello, welcome to my talk on the most useful Bernoulli's equation for the systems with pumps and turbines. In this talk, we will show how we can use the modified Bernoulli's equation to simply solve the hydraulics problem with pumps and turbines. The hydraulic systems are very important in our daily lives. We can see the hydraulic system everywhere, from the basic water supply to the appliances such as washing machines, electronic showers, etc. In my previous talk, we have talked about energy losses in the real piping systems, including the major loss and the minor loss. To maintain the water supply, we may need pumps to increase the pressure head. And in other applications, we may have turbines to extract energy out from the stored energy. So here, two types of important machines will be examined based on the modified Bernoulli's equation. The first type of the machine is the pump, which can be used for increasing the energy head to the fluid. For instance, to pump water to the water tower or to a high place as energy storage. The second type of the machine is the turbine, which is used for extracting energy out from the stored potential energy, such as from the reservoir of the hydraulic dams or from high places of the pumped storage systems. The first case is the hydraulic system with a pump. See in this drawing. The pump pumps water from the reservoir at a lower position to a tank in a higher position. Obviously, when the water is pumped into a higher position, the energy, here the potential energy, is increased. The increased energy must come from the pump. If we draw the energy grade line, EGL, we can see the grade line as this. And we also see there is a big jump, H pump, from here to there. So this is the head increased due to the pump. And if we draw the hydraulic grade line, it would be quite similar to the energy grade line. Here we can see, since in such a system, the pipes would be in a constant diameter. Thus, the velocity head in the pipe would be same. The modified Bernoulli's equation for such an application is given as this for the 2 points, 1 and 2. Here, HL is the total head loss in the hydraulic system, mostly happened in the pipes in the system. Here, the pump head, HHAM, is a positive value. This is in the left-hand side of the modified Bernoulli's equation. And the pump head can be calculated using this formula. Here, P pump is the power available to the pump, such as the shaft power from the motor to pump. And at the pump is the pump efficiency. For instance, the pump efficiency can be high as 80%. And m dot is the flow mass rate with the unit of kg per second. This is the flow chart of the hydraulic head for the system with the pump. Here we can see the hydraulic input here, and also we have the pump input, H pump here. At the right-hand side of the Bernoulli's equation, we have see this hydraulic output, this as well as the head loss HL here. In this slide, we examine an example of such a system. Here, a pump with a shaft power of 15 kW and an efficiency of 75% is used to pump water from reservoir to a tank through a constant diameter pipe, and the height of the water level from the reservoir to the tank is h 20 meters. If the hydraulic head loss in the piping system is 3 meters, the question is find the pumping flow rate of water and the pressure difference across the pump. For this problem, we are going to use this modified Bernoulli's equation for this problem. So in the analysis, at point 1 and point 2, the velocity V1 and V2 are both 0, and the pressure at the free surface here and here are both same as the atmospheric pressure P0. And the elevation difference between 1 and 2 given Z2 minus Z1 equaling h is 20 meters. And the head loss between 1 and 2 given HL equaling to 3 meters. In the solution, we can apply the modified Bernoulli's equation for point 1 and point 2 given in this equation. Here, since V1 and V2 are both 0, so these two terms would vanish, and these two terms would cancel each other because P1 and P2 are both same as the atmospheric pressure P0. Therefore, from this equation, we can obtain H pump equaling this. So we have H pump 33 meters for this problem. Now, since H pump can be calculated given as this, as we shown before in my previous talk. So here, P pump is the shaft power to the pump. Eta pump is the efficiency of the pump, and m dot is the mass rate. G is the gravitational acceleration. So based on this, we can calculate the pumping mass rate, m dot, given by this. So we have the answer for this, about 50 kilograms per second. So this equivalent to the flow rate Q given as this. The unit is liter per second. And also for the pump, the effective power would be equal to the flow rate times the pressure difference across the pump. Therefore, we can calculate the pressure difference across the pump, delta P, given by this formula, and we can obtain the answer for the pressure difference. It is 225.63 kPa. Alternatively, since the pump must provide a head H pump, so the pressure difference delta P can be simply calculated given as this: delta P equaling to rho G times H pump. So this gives the exact same pressure difference, 225.63 kPa. The second machine is the turbine in the hydraulic system. See the drawing here. We have the stored potential energy in the reservoir, and we can use the flow from the reservoir to the lower place through the turbine to extract the energy out. So if we draw the energy grade 9, it would be like this. Here we can see a big drop of the energy grade 9 here, H turbine, across the turbine. And this pressure drop is used to drive the turbine to generate the power. If we draw the hydraulic grade 9, it would be something like this. The modified Bernoulli's equation for the system with the turbine would be given as this for point 1 here and point 2 here. So we can see H turbine here is a positive value. It is in the right-hand side of the Bernoulli's equation. As we have shown before, H turbine is the hydraulic head available to the turbine, which is calculated given by this formula. Here, P turbine is the power output from the turbine. So this would be the shaft power from the turbine to the generator. Eta turbine is the turbine efficiency. It would be quite high as 90% or even more. And again, m dot is the flow mass rate, unit kg per second. So this is the flow chart for the hydraulic system with the turbine. So we have the hydraulic input from this side. So this represents the left-hand side of the Bernoulli's equation. And part of the hydraulic head, H turbine, here, and part of the head would be lost due to the friction in the turbine. And the majority of the head would become the power for the turbine output. And the rest of the hydraulic head would be the hydraulic output given here and the hydraulic loss HL here. So this part would correspond to the right-hand side of the modified Bernoulli's equation here. In this slide, an example, we have shown the application for the modified Bernoulli's equation for a system with a turbine. Suppose in a hydroelectric power plant, a flow rate of 100 cubic meter per second water flow from an elevation of 120 meter through a turbine for generating electric power. See the drawing here. Suppose the total head loss from point 1 to point 2 in this setup is 20 meter. And if the overall efficiency of the turbine generator is 80%, and the question is, what is the electric power output from this hydroelectric power plant? And what is the pressure difference across the turbine? So again, the problem will be examined using the modified Bernoulli's equation here for point 1 and point 2. So in the analysis, at point 1 and point 2, the velocities v1 and v2 are both 0, and the pressures p1, p2 are both same as the atmospheric pressure p0. The elevation difference is given by z1 minus z2 equaling to h as 120 meter, and the head loss HL is 20 meter. The mass flow rate can be calculated as m dot equaling to rho q. So it would be 100,000 kg per second. And the combined efficiency of the turbine and the generator is given by eta turbine times eta generator equaling to 80%. So in the solution, we apply the modified Bernoulli's equation for point 1 and point 2, given as this equation. Since V1 and V2 are both 0, so these two terms would vanish, and this term and this term would cancel each other because P1 and P2 are same. So from this equation, we can obtain H turbine given by this, and we can obtain H turbine would be 100 meter. Since H turbine is calculated given by this formula, so we can obtain the turbine power output is calculated by this formula. So the electricity generated by the generator would be given by the efficiency of the generator and the shaft power available to the generator. It is P turbine. So we have this expression, and we combine this together, so give the efficiency 80%, and times all this together, we have the answer for this. There would be 78.48 megawatt electricity generation. And the pressure drop across the turbine can be calculated simply as the delta P equaling P1 minus P2 equals H turbine times rho G. So this would be 981 kPa.